Okay folks, welcome back to another Math Notes. This is going to be Math Notes 2.1.2 Exponential Models. We're going to do a little review of how to write exponential equations and model real-world situations with them. Alright, let's go through the Math Notes here to start things off. Just remind everybody what the heck exponential equations are, why we use them, all that good stuff. So, situations that grow by equal factors or multipliers over equal intervals can often be modeled by exponential functions. An exponential function is a function in the form of f of x equals a b to the x. I'm going to highlight that. You need to know it. F of x equals a b to the x, where b is greater than 0 and not equal to 1, and a is not equal to 0. Note that the variable x is the exponent. That's what makes it exponential. If it's x to a number, then that's a polynomial function, like a parabola if it's x to the second, or a cubic if it's x to the third. So this is a number raised to the x value, which makes it an exponential function. All exponential functions of this form have the x-axis as the asymptote because f of x cannot equal 0. If you wanted to have a different asymptote, then we could either subtract or add a number to the x, which would shift the function left and right, or subtract or add our number to our y, which would shift it up and down. And we'll be doing more of that later. Since b to the 0 is 1, a is the value of the function when x equals 0, or the y-intercept. The base b is the multiplier. So let me sort of reword that a little bit by throwing some things here. So b is our multiplier. A, we're going to call our initial value. And if we graph that, our initial value would be where x equals 0, would be our y-intercept, okay? And typically what we're solving for, that f of x is our final value. It's our y, okay? So a is our initial value, b is our multiplier. So let's zoom out here a little bit. Okay, so for example, in the function y equals 3 times 2 to the x, a equals 3, so a, that's our initial value, b is our multiplier. Therefore, in the table and the graph at the right, 0, 3 is the y-intercept right here. Our initial value is 3. If we multiply 3 times 2, we get 6. If we multiply 6 times 2, we get 12. If we go in the opposite direction, half of 3 is 1.5. Half of 1.5 is 0.75. So in our graph, there's 0, 3, there's 1, 6, oh, 2, 12, going back in the opposite direction, we have negative 1, 1.5, negative 2, 0.75. So this is exponential growth because the function is increasing as we go from left to right, and the slope gets steeper and steeper as we go. To write an equation for an exponential function in the form of y equals ab to the x that passes through two given points, create a systems of equations by substituting one xy point into the equation y equals ab to the x, and then substituting the other point. Rewrite both equations in a equals form, set them equal to each other so that you can solve for a and b. Let's look at this example here. So for example, suppose the value of a rare stamp has increased exponentially. It was worth $14 2 years after Sean purchased it. So $14 2 years after Sean purchased it. And after 5 years, it was valued at $112. So we're going to know 2 points on this graph. If you think about it in terms of graph, we know that when x is equal to 2, y is equal to 14. We know that when x is equal to 5, y is equal to 112. So let's go on here. To model this situation, write the equation of an exponential function that passes through 214 and 5, 112. Create a systems of equations by substituting 214 and 2y equals ab dx, then substituting again with the other point. So we're going to plug in 2 for x, y for 14 in one equation, and then in a second equation we're going to plug in 5 for x and 112 for y. When we do that, we get these two equations. 14 equals ab to the second, 112 equals ab to the fifth. If we solve them both for a, then this equation becomes a equals 14 divided by b squared. This equation becomes a equals 112 divided by b to the fifth. And then since they're both equal a, we can set 14 over b squared equal to 112 over b to the fifth, which is what is done right here. So 14 over b squared equals 112 over b to the fifth. You can cross multiply so that we get 14 times b to the fifth equals 112 times b squared. Then we're going to divide both sides by b squared. And we're left with 14 times b to the fifth over b to the second equals 112. Remember that b to the fifth over b to the second simplifies to b to the third because of our exponential rules. When we divide both sides by 14, we get b cubed equals 8. Take the cube root of both sides, and b equals 2, which is our multiplier. So this stamp is doubling in value each year. That's what the multiplier means. Now that we know the multiplier, we're going to pick one of our other points. In this case, it looks like they picked 214 to plug in for x and y, and then use the new multiplier of 2 for our b to solve for a. So we go y equals ab to the x. We plug in 2 for x, 14 for y, 2 for b. We get 14 equals ab squared, or 14 equals a times 2 squared because the b is 2. And we solve finally for a equals 3.5, which now gives us our a value and our b value, which is enough to write the equation y equals 3.5 times 2 to the x, which will let us solve for the value of the stamp in any year. If we wanted to know what it was worth, in 500 years, we could just plug in 500 for x and it would be worth an awful lot of money. Okay, assuming that it continued to grow at that rate. So for your question at the end of this video, I have for her 15th birthday, Kylie's grandparents put $1,000 into a mutual fund for her. After 4 years, it was worth $1,238.82. Write an equation to represent the average exponential growth of the money. In other words, find a and b, and then plug it into y equals ab to the x. After you've found that equation, we're going to use that equation to predict future growth. If it continues to grow at this rate, how much will it be worth when Kylie turns 55?